So again, just to sort of go over each of those things in a little bit more detail, as I said, the ROM code is built into the system on chip. It's immutable. It is the first code that's executed at power on, as I said, right? So the important thing is that the starting address of the ROM must be connected up in the hardware itself, such that when I switch on the system, the default value of the PC that comes up must point to the starting address of that ROM, right? And once I have done that, it will basically do a very basic kind of stuff, initialize clocks and maybe some kind of IO. Mostly what is required to maybe turn on and off a few lights, right, to make systems blink just to show that there is a sign of life from the system. But after that, its job is not even probably print any messages on the screen, right? That's fairly advanced by itself. What it does is load the secondary program loader, SPL, from boot media. As I said, extremely limited capacity, probably tens of kilobytes at most. Okay. Now, by the way, one thing to keep in mind over here is this sequence that I have talked about over here is primarily targeted at ARM processors. Now, your PC does a very similar kind of mechanism, except that we don't have SPL and U-boot. Instead, we have what's called the BIOS, right? So the BIOS and the UEFI. BIOS is the basic IO system, and UEFI is, I think, the Universal Extensible Firmware Interface or something like that. So it's basically a more complex firmware interface that is capable of doing a bit more than what these can do, right? So it gets to the point where it does a lot of initialization, and then those of you who have actually installed Linux on your PCs would have seen that there is this thing called GRUB, right, the Grand Universal Bootloader, which gets installed on the main disk, and when you switch on the system, it comes and waits over there and says, okay, select which kernel to boot and so on. U-boot is sort of playing the role somewhere of, partly the BIOS and partly of GRUB, which takes care of actually loading the kernel. From this point onwards, where you have got to the kernel itself, it's pretty much the same, whether you are on a PC or on ARM. So, okay, now that the ROM code, we have established that it's very limited capacity and cannot do very much. Its main job was to load in the SPL, the secondary program loader. Now this is also small, tens, maybe hundreds of kilobytes at most, right? But that's okay, because many of the ARM SoCs typically have a very common value is somewhere around 256 kilobytes of on-chip SRAM. It's sometimes called the OCM, or the on-chip memory, right? Now you may have less, in which case your SPL has to be even smaller. But it doesn't have to do very much. What it has to do is basically initialize the DRAM controller. This is crucial, because up to this point, the only memory that you have access to is your on-chip memory. And if we say that your on-chip RAM is very limited in capacity, there's not much you can do. But once you initialize DRAM, you suddenly have access to hundreds of megabytes or possibly gigabytes of RAM. Okay. Once that's done, good news, you can basically go activate whatever storage, typically an SD card, right, and load U-boot from there into some location in DRAM and transfer control. Now this transfer control is something we keep talking about. All that means is I jump to the starting point of that function. Okay. Now the SPL is typically under user control to some extent, meaning that you can write some of the code that goes into the SPL, right, but it's still very limited capacity, so you are typically not expected to change it around too much. Okay. So just before we proceed further, one thing that I wanted to point out, there is one thing which you will probably notice when you are dealing with the boot flow of processors. Most ARM processors go through exactly the sequence that I showed just now, right? You have the ROM code, the secondary program loader, U-boot that we will get to in a moment, finally load the kernel and then run init. Now in the case of Xilinx and their Zynq FPGAs, there is an ARM processor, but Xilinx has basically gone and modified the boot process slightly, because it sort of makes sense. They know that their ARM processors have something a little extra special, right? What is that? There is an FPGA fabric, right, the PL, the programmable logic, that may or may not need to actually be programmed. Okay. So what they do is, instead of having the secondary program loader, they have the boot ROM, and then they have something called the FSBL, or the first stage bootloader. Essentially the same thing with a different name. The important thing is that this first stage bootloader is usually generated by the Vivado or Vitis tools that you actually use in order to create your hardware, which means that it is hardware design aware, right? It knows about the components that you have got in your bit stream or your platform as they call it, right, and generates an FSBL that is aware of that. Okay. After that, the rest of it, it still goes through to U-boot, then finally the kernel and init. Okay, so this FSBL is something Xilinx specific, and what happens is it is generated by Vivado or Vitis, right, depending on which part of the SDK you are using. The key responsibilities of this are essentially the same as what the SPL would do, right? It has to sort of bring up the clocks, MIOs, peripherals. In other words, see, terms like the PS, the processing subsystem, right, and the PL are Xilinx specific. General ARM processors do not have a concept of a PS. Everything is the PS as far as they are concerned. The DDR controller initialization, this is also something which is, after all, they are part of the Xilinx FPGA fabric, so it has a fairly standardized initialization process. The interesting thing is the FSBL can optionally load an FPGA bit stream. This is something which normal ARM processors would not have. And then finally it hands off to the U-boot. Okay. So the key differences between the FSBL and generic SPLs are it's hardware design aware and generated from the Vivado project. Okay, which means it contains board specific initialization and it can program the FPGA before U-boot happens if necessary. This is a choice which we will talk about briefly later, right? And one file that you will find typically getting created when you are going through this process of the FSBL is this file called boot.bin, right? This contains pretty much everything that we are talking about, but put in a standard binary format. It contains any headers required for the boot ROM, the first stage bootloader code, an optional bit stream. It's optional because you may choose that you just want to sort of boot up the system and not really program the bit stream there, and then U-boot. So this boot.bin in other words contains everything that is required to get to the point of actually loading the kernel. And Xilinx provides tools that help you to generate this in a sort of semi-automated way.